Hello, and welcome to the 13th webinar in our Lunch, Learn, and Dance Wellness webinar series, Norm Awareness. My name is Lynn McDonald. Joining me in the chat room is Maria Costa. Anastasia from Salem Dance Company will be leading us in dance beginning at 12:30 Eastern. Let's take a moment to go over the functionality of the Zoom webinar. The audio and video will be from the presenters only. We have found that although you can access the audio through the computer or telephone, the quality of sound tends to be better when listening from a computer. There is a chat feature where people can discuss. If you would like, take a moment now to say hello and where you are from. If you have questions arriving from the content, please enter them under the Q&A section. As the webinar is only a half hour in length and is immediately followed by our dance session, time may not permit for me to answer them during the webinar. The answers will be posted on our website, along with a link to the video recording and a copy of the slides. This can be found under Education Webinars. I will be sending a confirmation of attendance email after the webinar and will include a link to the page with that communication. I will also include the topics covered and length of time spent in the webinar, as some people have requested this to send to their professional association. Lastly, I have automatic closed captioning enabled in the slide presentation. If they are being blocked by your Zoom controls, you should be able to select another way to view the webinar in Zoom, which makes them easier to see. The acronym NORM stands for Naturally Occurring Radioactive Material. To understand NORM, today's webinar will start with a review of what ionizing radiation is, quantities and units related to radiation health risks as they relate to NORM, and background radiation. These topics are each covered in more detail in other webinars in the series, including Understanding Radiation and Health Effects of Exposure to Ionizing Radiation. We will then look at sources of NORM, both terrestrial and cosmic, ICRP recommendations regarding NORM, regulation in Canada, and the Canadian NORM guidelines. The science concepts are presented at a conceptual level, and regulation is presented as an overview and where to find more information. You are legally responsible to follow the full regulations applicable in your jurisdiction, which are more comprehensive. To understand radiation, you must understand some chemistry and physics. Physicists study the interaction of matter and energy. Matter is made of small particles called atoms. All matter has mass and takes up space. Energy is the ability to create change in matter. It has many different forms, but we often talk about two types of energy: kinetic, or the energy an object has due to its movement, and potential, which is stored energy. When energy is transferred out in straight lines, we call it radiation. It can take the form of beams of particles or waves. All matter is made up of atoms. The atom is made up of three types of particle: the proton, which is positively charged, the neutron, which is neutral, and the electron, which is negatively charged. Protons and neutrons are strongly bonded together to form the nucleus of the atom, and the electrons orbit around it. When we talk of nuclides, we are referring to an atom with respect to its nuclear properties, its number of protons and neutrons, and its energy state. Isotopes are nuclides with the same number of protons, but they can have different number of neutrons. Elements are determined by the number of protons in the nucleus, so isotopes have similar chemical properties, even though the stability of their nucleus can differ. Excuse me one moment. Most nuclides in nature are stable isotopes. This means that their nuclear forces are strong enough to hold their nucleus together indefinitely. But some isotopes are unstable. Their nuclear forces are not strong enough to hold the nucleus together indefinitely. These unstable atoms want to become stable. To do so, they emit radiation in the form of particles of matter or massless uncharged bundles of energy called photons. We call these unstable isotopes radionuclides. When they emit particles of matter from their nucleus, they become a different element, which may also be radioactive. The process of radioactive decay will continue until the resulting atom is stable. Some decay series have quite a number of steps, while others have only a few. For the emitted radiation to deposit its energy into material, it must interact with matter in some way. If the radiation carries enough energy, it can knock one or more electrons out of their orbit around the nucleus. Matter has a tendency to move towards stable, low energy states. As a result, atoms will typically either be electrically neutral or form molecules that are electrically neutral. An electrically charged atom is called an ion. When radiation has enough energy to knock electrons from orbits, it's called ionizing radiation. Radiation that does not have enough energy to remove electrons from their orbits is called non-ionizing radiation. We'll focus today's sessions on ionizing radiation, as all radiation that comes from nuclear sources is ionizing. There are many sources of radiation that do not have enough energy to ionize atoms. If they have health effects, they are related to heating or a process called photochemical effects. These are regulated provincially or territorially in Canada. There are two sources of ionizing radiation: radioactive atoms and human-made machines. Examples of such devices are X-ray units, which include CT scanners and particle accelerators. There are several types of ionizing radiation. Alpha particles, beta particles, and gamma rays are all emitted from the nuclei of radioactive atoms. Neutrons are liberated during the fission or breaking of large atoms like uranium. X-rays are produced by machines. All these types of radiation have enough energy to knock electrons out of their orbit around the nucleus of the atom. These are regulated federally in Canada, as they have more potential for harm than non-ionizing radiation. As our topic here today is naturally occurring radiation, we will be focused on radiation produced by radioactive atoms. First, let's look at some of the quantities and units related to radioactive nuclides. One way to measure the radioactivity of a substance is through its activity. Activity is the rate of radioactive decay, in other words, the number of radioactive decays which occur per unit of time, for example, per second. The unit of activity that is used in the SI system, the system of units used in Canada, is the becquerel, named after the person who discovered radioactivity, Henri Becquerel. A becquerel is simply one radioactive decay per second. The old unit, still in use in the United States, is the curie. One curie is equal to 37 billion becquerel. The activity of 1 milligram of uranium-238 is 10 becquerel. The activity of 1 milligram of americium-241 is 100 million becquerel. The drastic difference in these activities is related to their half-life. An isotope's half-life is the time required for a radioactive sample to lose 50% of its activity by radioactive decay. Each radionuclide has its own unique half-life, regardless of the quantity or form. It does not matter if it's a solid, liquid, or gas, a pure element, or in a compound. No physical or chemical process can alter the half-life of a radioactive element. The effects of radiation on a cell, tissue, organ, or human depends on how much energy is absorbed into it. A dose of ionizing radiation is a measure of how much energy is given to the body from the radiation and is used to indicate the effect it may have. There are three common ways dose is reported: absorbed dose, which is the energy given to the body by radiation per unit mass, measured in gray; equivalent dose, which also takes the type of radiation into account, measured in sieverts; and effective dose, which additionally considers the sensitivity of different tissues to radiation, which is also measured in sieverts. Depending upon the type of radiation, the way it is being used, and the regulator, what is monitored and reported varies. A deterministic effect, also called a tissue reaction, is one which will definitely occur when radiation exposure has exceeded a certain threshold. An example of a deterministic effect of radiation is a radiation burn or the development of cataracts. Deterministic effects do not accrue below acute exposures to approximately 250 milligray. With an acute radiation exposure of 250 milligray, one might begin to observe temporary changes in the blood cell counts within a few days. To observe a radiation burn, One would have to receive an acute radiation exposure of approximately 5 gray. This is a very large dose. The symptoms of radiation sickness are seen in patients undergoing radiation treatments for cancer. These people are exposed to high doses of radiation concentrated in the area of the tumor in order to try and kill the cancerous cells. But the side effects of these high doses of radiation are things like hair loss, nausea and vomiting, fatigue, and general malaise. It is unlikely that anyone working with NORM would receive acute radiation doses high enough to cause deterministic effects. Cataracts are a deterministic effect which can result from chronic low dose exposure to ionizing radiation and other environmental agents. The word stochastic is used to describe an event that increases in frequency under certain conditions, but you cannot ensure it will happen under those conditions. There's no threshold under which the risk disappears. The risk of the effect increases with increasing exposure. Radiation exposure increases the likelihood of developing cancer. The greater the exposure, the greater the likelihood, but we cannot be certain that the effect will or will not occur. For that reason, we call it a stochastic effect. For adults, the risk of developing a fatal cancer as a result of exposure to radiation is approximately 4% per 1,000 millisieverts. Consider a person who worked for 50 years and received a 20 millisieverts of dose per year. This person's total lifetime radiation dose would be 1,000 millisieverts. This person will have an extra 4% chance of developing a fatal cancer. In Canada, approximately 25% of people develop a fatal cancer in their lifetime. So the risk of developing a fatal cancer to the adult who received a 20 millisieverts dose of ionizing radiation a year for 50 years becomes 29% instead of 25%. This means that if you took two groups of 100 people, one which had no additional radiation dose above what we receive as part of day-to-day life, and the other who had received 1,000 millisieverts additional dose over a long period of time, the first group would have on average 25 people die from cancer, whereas the second group would have 29. Being exposed to radiation increases the development of cancer, or the risk of developing cancer, but getting cancer is not a definite consequence of being exposed to ionizing radiation. Whether or not you work with sources of ionizing radiation, you are still exposed to it daily. Although most material we encounter is not radioactive, the Earth's soil, water, and air all contain radioactive isotopes. We regularly ingest or inhale trace amounts of radionuclides as they are found throughout nature. We are also exposed to ionizing radiation from the sun and outer space. The Earth's atmosphere and magnetic field protect us from most of this radiation, but the atmospheric protection is less at higher altitudes. The average Canadian is exposed to 1.8 millisieverts per year from background radiation. In some parts of the world, that number can be over 200 millisieverts per year, although that is an extreme. We are also exposed to ionizing radiation during certain medical procedures used for diagnosis and treatment. For example, X-rays, CT scans, radiation therapy, and nuclear medicine procedures. These include dental X-rays. The range of dose of radiation varies widely, and it is up to the physician to balance the need for the procedure with the risk associated from the exposure to radiation. So where does NORM come from? Cosmic rays from space, a natural source of ionizing radiation themselves, interact with atoms in the atmosphere to produce radioisotopes such as carbon-14, beryllium-7, and tritium. Naturally occurring radioactive material has existed in the Earth's crust since it was formed. Uranium-235, uranium-238, and thorium-232 have half-lives ranging from 710 million to 14 billion years. They each have decay chains that contain many different radioisotopes, so as the uranium and thorium decay, these others are eventually produced. Potassium-40 is another major source of natural radiation that has been around since the Earth was formed, but it decays to one of two stable nuclides. It and other single decay radionuclides do not have a decaying chain in the same way as the isotopes of uranium and thorium. At a previous point in history, the neptunium decay chain was a source of naturally occurring radioisotopes in the same way, but as its half-life is 2.3 million years and the Earth is 4.5 billion years old, today the amount found naturally is negligible. Natural radioisotopes are present throughout Earth's crust, mostly in low concentrations. Some of these radionuclides are soluble in water or in gaseous forms, so the atmosphere and oceans contain radioisotopes as well. Norm can come to the surface naturally, for example, when radon gas escapes directly to the atmosphere or is dissolved in the groundwater and then released later when the water is agitated. Human activities such as mining or oil and gas extraction can bring people into contact with higher levels of norm than a typical person because the people are being asked to work in places with higher than usual amounts of norm. Some human activities can cause norm to become concentrated. For example, the coal ash from coal burning power plants has higher concentrations of norm than the coal because most of the radionuclides are left behind during burning. If the activity is concentrated due to human activity, the material produced is considered T-norm, technologically enhanced, naturally occurring radioactive material. There are several industries known to have possible norm-related radiation exposure. Mining and the production of mined materials have a risk of norm-related radiation exposure either due to working with norm directly or due to the wastes produced. Industries involving large amounts of water in enclosed areas, such as water treatment, are also a possible source of norm-related radiation exposure, mainly due to radon. Other industries which may have norm-related exposure to ionizing radiation include the production and use of some consumer products, energy production, tunneling and underground work, as well as metal recycling. In fact, many recycling facilities have radiation detectors at their facilities to prevent radionuclides, norm or otherwise, from entering the recycling stream. Depending upon the work being performed, the risk of internal or external exposure from norm or T-norm varies. Exposures could come from performing maintenance on equipment with a buildup of norm in the form of slag, scale, or sludge. Radon is a concern in enclosed spaces, especially when working underground or in facilities that process water. Airborne dust is a possible hazard, particularly in mining and milling operations. There are a number of international bodies involved in the development of radiation protection guidelines. The IAEA explains their relationship as shown. UNSEER reports typically summarize the latest knowledge on the effects of radiation. The ICRP puts out recommendations for protection, and the IAEA documents tend to provide essential principles and requirements for their implementation. ICRP Publication 142 speaks to the radiological protection from norm in industrial processes. The main points of the document are: exposures from norm are controllable through justification of taking protective actions and optimization of protection. Norm presents a chronic low-dose risk and not a short-term emergency risk. It is recommended to have integrated and graded approach for protection. Reference levels for workers, excluding radon and thoron, should reflect the distribution of exposures and would typically be less than 10 millisieverts. Reference levels for the public should also reflect the distribution of exposures, but generally be less than a few millisieverts. And radon and thoron exposures should rely on measures recommended in the ICRP Publication 126, Radiological Protection Against Radon Exposure. We have a webinar specifically on radon for more information. The ICRP documents are used by local regulators around the world to create legislation and guidance for their jurisdiction. The CNSC is Canada's nuclear regulator. NORM is exempt from CNSC jurisdiction under the federal regulations for the use of radioactive material, except when NORM is associated with the development, production, or use of nuclear energy, and some transport situations. Thus, norm jurisdiction is provincial or territorial. Provincial occupational health and safety regulations generally do not specifically mention norm, so to provide consistency across these jurisdictions, the Federal Provincial Territorial Radiation Protection Committee has produced the Canadian Guidelines for the Management of Naturally Occurring Radioactive Material, NORM. To quote the document, the basic principle of these guidelines is that where workers or the public are exposed to additional sources or modes of radiation exposure because of activities involving norm, the same radiation protection standards should be applied as for CNSC regulated activities, end quote. The guidelines are based on most recent international standards recommended by the International Commission on Radiation Protection. The Canadian Norm Guidelines provide principles and procedures for detection, classification, handling, and material management of norm in Canada, along with guidance for compliance with federal transportation regulations. If a workplace is one of the norm-prone industries, an assessment should be carried out. The steps to do so are to estimate doses to workers and members of the public, determine the program classification, classify workers if needed, and implement radiation protection programs as applicable. People do not possess any sense organs that can detect ionizing radiation. We cannot see, hear, feel, taste, or smell ionizing radiation. We must rely entirely on instruments for the detection and measurement of radiation. The assessment of norm radioactivity in a workplace require the use of instruments to measure the amount of ionizing radiation present. There are two main categories of radiation measurement instruments used in radiation safety: dosimeters, which we'll discuss later in the webinar, and survey instruments. Survey instruments measure the rate of radiation events, usually as a count rate, for example, counts per minute, radiation dose rate, for example, microsieverts per hour, or an exposure rate, for example, milliroentgen per hour, which is an imperial unit. Survey instruments are usually handheld and battery operated. Multi-purpose survey instruments have different detector probes to allow them to measure all types of radiation. The different classification of workers, it depends upon the job function and associated probability of ionizing radiation exposure. The categories are occupationally exposed workers, or OEW, which are employees who are exposed to norm as a result of their regular duties; incidentally exposed workers, which are employees whose regular duties do not include exposure to norm; and members of the public, which are persons who have no occupational exposure to norm. The dose limits for each classification of worker within the norm guidelines are shown. They are in alignment with the CNSC dose limits for nuclear energy workers. Although these dose limits are in place, under the optimization principle, doses are to be kept as low as reasonably achievable, or ALARA. This means that doses should be kept well below these limits, and if workers are approaching these limits, the radiation protection program should be reassessed. Requirements for the management of norm are based on likely doses, including doses from external gamma exposure, internal doses from norm intake, and radon gas. If doses may exceed 0.3 millisieverts per year to public or workers, a site-specific assessment should be done. There are 4 norm program classifications provided, each with different levels of required radiation protection measures. A flowchart is provided to help determine the classification. Let's break the flow chart down. For a workplace to be considered unrestricted, doses to public must be assessed at less than 0.3 millisieverts per year, and doses to workers assessed at less than 1 millisievert per year. No further action is needed to control doses or materials. If the assessed dose to the public is greater than 0.3 millisieverts per year, but less than 1 millisievert per year for both the public and the workers, the program is classified as norm management. Under this classification, public access is restricted. The norm management program may include incidentally exposed worker access restrictions, shipping and/or material management, and/or changes in work practices to reduce doses. The program is assessed as dose management when the assessed dose to the worker is greater than 1 millisievert per year, but less than 5 millisieverts per year. The norm management program is to include worker notification of radiation sources and the reduction of dose through engineering controls, work procedures, protective clothing, and training. It should also include a worker radiation dose monitoring program, which could involve estimates of dose based on the time spent in an area and area dose rates or monitoring with dosimetry, as well as reporting worker doses to the National Dose Registry. Radiation protection management is needed when the assessed dose to the worker is greater than 5 millisieverts per year. Norm management is to include a formal radiation protection program to keep exposures as low as reasonably achievable through management control over work practices, personnel qualification and training, control of occupational and public exposures, and planning for unusual situations. Workers with possible exposures of 5 millisieverts per year should be on a dosimetry program using CNSC licensed dosimetry service provider. The employer must also provide personal protective equipment and clothing and develop work procedures to reduce worker dose and spread of contamination. Dose management and radiation protection management programs have requirements for measuring and reporting doses. We have no sensors to detect ionizing radiation. Exposure to it can lead to health consequences that appear days or years later, depending upon the strength of the dose and the tissue receiving it and the type of damage incurred. For this reason, dosimetry is used to determine how much energy radiation has been deposited into an individual. The type of dosimetry program used depends upon the type of radiation expected to be encountered and the part of the body expected to receive it. A dosimetry program for external exposures would be different than that for internal exposures. If both types of exposures might be expected, then both types of program would be needed. For more information on dosimetry, please see the webinar PPE and Dosimetry. If the program classification is greater than unrestricted, periodic reviews must be taken. These reviews must determine if changes to systems have occurred which may affect worker doses and to monitor the effectiveness of the norm program. The frequency depends on the ability of conditions to change and the norm program in place. The norm guidelines provided are based only on the radiological properties of the isotopes. Care must be taken to manage material properly, including requirements based on other hazards such as chemical toxicity. Prior to transport, you must assess norm to determine the radioactive content or the activity concentration. Tables are provided with activity concentrations for exempt materials for ease of reference. Norm transport falls under federal regulations, Packaging and Transport of Nuclear Substance Regulations 2015, and the Transportation of Dangerous Goods Regulations, if the activity concentration of norm is greater than 10 times the activity concentration for exempt material values, and the material is transported off-site over public or privately owned land. If the amount is below 10 times the exemption quantity but greater than unrestricted release DRLs, a transport manifest is completed containing the descriptive naturally occurring radioactive material norm. The package should be securely packaged to prevent release during transport, and you must account for any other potential hazards property of the material. There are no radioactive placards or labels affixed to the vehicle or exterior of the package. Norm contaminated waste does not go to a regular landfill if it exceeds the release limits given in the guidelines. According to the CNSC, there are currently provincially licensed norm disposal facilities in Alberta, Saskatchewan, and British Columbia. If you work in one of the mentioned industries, but do not know if the guidelines have been considered, your first point of contact would be your occupational health and safety representative or committee member. You should also check for your provincial or territorial regulations to see what is expected in your jurisdiction. For federally regulated workplaces, the jurisdiction is the federal government under the Canada Labor Code. If you are still unclear or have concerns about NORM or any other radiation safety topic, you can also contact us at the Radiation Safety Institute of Canada. We have a toll-free information service to support questions from employers, workers, and the public with respect to both ionizing and non-ionizing radiation safety. We also provide consulting services for those who might need support in developing a radiation protection program and related services, including radiation surveys. If you have any further questions about ionizing or non-ionizing radiation, please feel free to contact us toll-free at 1-800-263-5803 or by email at info@radiationsafety.ca. You can also visit us on the web at www.radiationsafety.ca or find us on Facebook.
To register, go to www.radiationsafety.ca/services/webinars.